Hi everyone. Let's go ahead and solve a trig equation using our new toys, our new tools, these additional trig identities. Let's solve sine of x minus cosine of 2x equals 0. Now, don't do anything foolish like taking out that 2. Don't engage in wishful thinking. We're going to apply an identity, a double angle identity for cosine. Now, the way that some students might approach this, and then I'll show you a more efficient and concise way. The way some students might approach this is, well, let's see, cosine of 2x, yeah, I remember that. The cosines minus the sines. The cosines minus the sines. Cosine of 2u was cosine squared of u minus sine squared of u. And you could try that. Please remember what? When you put in that expression, when you substitute in cosine squared of x minus sine squared of x, first of all, it's an x, not u. But more importantly, grouping symbols. Remember, whenever you perform a substitution, be prepared to put grouping symbols, especially when there's a minus sign in front. If there's a plus sign in front, then this isn't such a big deal. But if there's a minus sign in front, oh yeah, we're going to need grouping symbols. Or distribute directly. But I'd recommend grouping symbols. Then we can distribute the -1 in here. Sine of x minus cosine squared of x, again, plus sine squared of x. You've flipped the sign there, equals 0. And then you go, well, wait a minute. One of these things does not look like these others on the left side. How can we make cosine squared of x look more like sine squared of x? Well, Mr. Pythagoras. And again, grouping symbols would help. Cosine squared of x is what? From Mr. Pythagoras, a Pythagorean identity, it's 1 minus sine squared of x. But since it's more than one term here, and since we're following a minus sign, we need these grouping symbols. We distribute sine of x minus 1 plus, it's a plus, sine squared of x plus sine squared of x equals 0. Over here, what's apple plus apple? Or what's u plus u? It's twice apple, or 2u. 2 sine squared of x, and then plus sine of x, and then minus 1 equals 0. And we have here a nice quadratic in sine of x. So that's the way that a lot of students would approach it, but there's actually a more efficient way of getting this. I'll go back up to here. Cosine of 2x. Remember, we had 3 double angle identities for cosine of 2x. So if you're able to figure them out, or if you've mind dumped them, which one would work best? We have 2 other identities that could work. And I think we could use the one with sine squared of u here. So instead of this big daddy identity here, let's use cosine of 2u equals 1 minus 2 sine squared of u, where we're basically doing our Pythagorean work already. This already incorporates some of the Pythagorean work we did in here. So instead of basically rederiving this, hopefully you can remember this or get this from your mind dump sheet and apply it directly. So then if you do that, you would get sine of x minus the quantity. Again, we need grouping symbols here. Instead of cosine of 2x, let's use 1 minus 2 sine squared of x. 1 minus 2 sine squared of x. I'll write the 2 in here. And then when you distribute the -1, you get sine of x minus 1 plus 2 sine squared of x. And then when you combine this stuff, with the sine of x, remember just the sine of x is the other piece here. When you combine these pieces, all right, so we get, no, we didn't have to combine. I already combined the sine of x piece. Okay, so we combine the sine of x with this stuff over here, right? Okay, but we already put in the sine of x here. All right, so the left-hand side becomes 2 sine squared of x plus sine of x minus 1. Okay, exactly what we got over here. But this is more efficient if you use the more appropriate identity right off the bat. So on the one hand, even though this might seem more immediate, then you have to actually do some more work, and you kind of rederive this structure along the way. So it takes more steps. Whereas if you strategize and if you realize which identity would really work best, if you can get that best identity, then your work goes a bit faster. But on homework or exam, I'd accept either approach. Now at this point, a substitution might be appropriate. You don't have to do a substitution. I don't in my notes, but we can do a substitution. Let u be sine of x. And then we can get a quadratic in u. All right, so we apply the substitution. Again, here I didn't apply it. You can go ahead and factor this directly. You don't have to do a substitution, but I think people might recognize this better. 2u squared plus u minus 1 equals 0. We have a square here. And we can factor this old school. We can factor it as 2u minus 1 and u plus 1 and equals 0. Of course, in order to apply the zero factor property, we have to isolate 0 on the right side. We have a zero factor property. If you're going to use a factoring method, we ultimately need a 0 on one side here. All right. So 2u minus 1, or subbing back, 2 sine of x minus 1, and then this factor, u plus 1, or sine of x plus 1. So if you do a substitution, then you would go to here as your next step, or instead of going to here, you could solve for u directly over here, right? So we can get our two cases. 2u minus 1 equals 0. You add 1 to both sides. And then divide by 2, and we get u equals 1/2. So again, here I set 2u minus 1 equal to 0. All right. Add 1 to both sides, we get 2u equals 1. Divide both sides by 2, u equals 1/2. And that's going to lead to case 1. I'll put this in red. And then over here, u plus 1 equals 0. Well, that's pretty straightforward. U plus 1 equals 0. Subtract 1 from both sides, u equals -1. So we need sine of x to be -1. That's case 2. I'll put that in blue. All right. So you can either substitute and solve for u directly, or don't bother substituting. Just factor directly in terms of sine of x. Set each factor equal to 0 and solve for sine of x, which is like solving for u here and here. Either way, we get two cases. One case where sine of x is 1/2, and one case where sine of x is -1. And again, you could do it either way. You can either do it through a substitution or just factor directly in terms of sine of x. But either way, these are going to be our two cases. We're going to solve these two smaller trig equations, but don't go too fast. Take a step back and think these through. But we have two cases. All right. Case number 1, sine of x equals 1/2. That was in red here. Sine of x equals 1/2. We're going to solve this trig equation. Don't rush. You can get this, but don't rush. I'll put this in red, since that's our color for this case. All right. First of all, we agree that 1/2 is a legitimate sign value. It's in the range of sign. It's in the closed interval from -1 to 1. In fact, it's a known special sign value. We can get exact solutions coming out of this equation. We won't have to use inverse sign or arc sign notation. We won't need decimal approximations. Okay, so, well, first of all, the arc sign of 1/2 will be a solution. The sign of what is 1/2? In quadrant 1, what's the acute reference angle here? Sine of 30 degrees is 1/2. Although here, when you're solving equations, going back to radians may be more helpful. Pi over 6, that's going to be a key solution for this equation. And more importantly, it's going to be the brother, the co-reference angle for all the solutions to this equation. So pi over 6 and all its coterminal twins will be all the solutions we need from quadrant 1. But in what other quadrant is the sine function, sine, positive in value? Where is sine positive? In quadrant 1 and also quadrant 2. All right. And actually, this guy is kind of flat, right? Let me indicate that. He's kind of flat. All right. Although the y-coordinate here is 1/2. So what's a key brother for this point? Although, as we'll see later on, it turns out that we don't even need a representative for this point. But many students would like to know what a key representative for this point is. I think many students would choose pi minus pi over 6, the supplementary angle. I think many students would choose 5 pi over 6, which is the most famous representative for that point in quadrant 2, the most famous brother in quadrant 2. So if you wanted to solve this equation individually, right, well, it would be, if this were the original question, the set of all x in the reals such that x equals pi over 6 plus 2 pi n, or x equals 5 pi over 6 plus 2 pi n. With the plus 2 pi n's, where n is integer, we're picking up all the coterminal twins for both these angles. So this is basically giving us all the solutions for sine of x equals 1/2. But remember, there's a second case where sine of x equals -1. So this picture is just reiterating this picture here. Again, as I'll show you later on, it turns out we didn't even have to identify the 5 pi over 6. There's a clever way of avoiding having to know this. Although you should know 5 pi over 6 is the key rep for this point. All right, off to the second factor. All right, sine of x equals -1, basically. All right, in blue. -1 is in the range of sine. It's a sine value. And where is the corresponding point on the unit circle? Sine of x translates to the y-coordinate, the vertical coordinate. It's kind of confusing because cosine of x is actually the x-coordinate on the circle. X is an angle here, remember? X represents an angle here. For what angle is sine equal to -1? Well, there are a couple of reps we could use for this point. We could use 3 pi over 2, the most famous positive representative, or its most famous negative coterminal twin, -pi over 2. I'd accept either. And I am asking for all real solutions. If I'm not saying otherwise in the problem, I want to find all real solutions. The implication is that we solve this on R. I want all real solutions. All right, so from this south pole, we get this. X equals 3 pi over 2 or -pi over 2 or any coterminal twin. These are the two most popular choices. 3 pi over 2, let's say, plus 2 pi n, where n is integer. We want to pick up all the coterminal twins for that south pole. Okay, so if we bring it all together, you could say the solution set could look like this. The set of all x values in the set of real numbers such that x is of the form pi over 6 plus 2 pi n. I'll remind you where these are. Pi over 6 plus 2 pi n. So all the reps for that point. Or x equals 5 pi over 6 plus 2 pi n. So all the reps for this point. Or x equals 3 pi over 2 plus 2 pi n. All the reps for the south pole, where n is integer. And I would accept this as a final answer. However, it turns out here, there's a remarkable symmetry, which I wouldn't require you to use. But one nice result from this symmetry is that it turns out that you only need one representative for any of these points. And in fact, a rep for the south pole, like 3 pi over 2 or negative pi over 2, may be the most convenient and accessible. Because some students might be puzzling, wait a minute, the sine of what is 1/2? Now, I hope you can figure that out. But let's say you're stressing out, right? Really, we just have to worry about a rep for any one of these points, like this point. We could take 3 pi over 2 or negative pi over 2. And then we rotate. Let's draw in these radii, these line segments. I call this the peace symbol pattern. If you remember the 1960s, symbols from the 1960s peace movement. I guess we could relate this to radioactivity nowadays. But take a look and check this, work this out. A third of a revolution about the unit circle. A third of a revolution about the unit circle. A third of a revolution back to the South Pole. It turns out that we can get all real solutions for the equation by starting at any representative for any of these 3 points. 3 pi over 2 or negative pi over 2 could be the easiest ones to use, corresponding to South Pole, and then revolving either counterclockwise or clockwise by third revolutions. A third of a revolution, 2/3, 3/3 is one full revolution. Going by thirds of a revolution. What is a third of a revolution? Well, how much is in a full revolution? A full revolution is 2 pi radians. What's a third of a revolution? Counterclockwise, 2 pi over 3. So what do? Take any rep for any one of these points and add 2 pi over 3 n, where n is integer. This counts the number of third revolutions. If n is positive, we go counterclockwise. If n is 0, we stay put. If n is negative, we go clockwise. A more efficient form, the peace symbol, or the radioactivity symbol. Start at any representative for any point. A rep for the South Pole may be easiest because a lot of people might forget pi over 6, or it might take them a while to figure it out. Again, I hope you can figure it out quickly, but still, 3 pi over 2 may be easier. And you go around by third revolutions. Okay. In fact, here, if you want to have the nicest form in terms of show, pi over 6 may be the best looking, right? It may be the Brad Pitt of these angles, even though 3 pi over 2 might be easier to find. The set of all x in the real such that x equals, you could take any rep for any point. 3 pi over 2 might be the easiest to figure out, maybe negative pi over 2, but pi over 6 is probably the nicest one to write. So in textbooks, they might use pi over 6 because it's the prettiest of them. It's the best looking, the Brad Pitt of these 3. Pi over 6 plus, and then again, a third of a revolution is 2 pi over 3, n, where n is integer. N counts the number of third revolutions, and if n is negative, you go clockwise. Whoa, whoops. I made this mistake earlier. X is in the reals. The set of all x in the reals, such that n is in the set of integers. Okay, I didn't make that mistake earlier, did I? Wow, I did. This is z. Okay, that's z. Okay, so be careful. The set of all x in the reals, such that n is in z, the set of integers. I've made this mistake before. So this is the most efficient form for the solution set, but I would not penalize you. I would not mark you down for not giving me the most efficient form. Okay, but give me something correct and reasonable. Something like this I would accept. It's correct and it's reasonable. Don't try to start out listing individual angles, a whole bunch of individual angles. That would not be reasonable. You'd have to use ... or something. There are infinitely many solutions. Okay. Next up, a more exotic application. Using a right triangle technique to express this strange expression algebraically. Next time.